how it fits into our existing models. Lewis suggests that while equations can be written for various phenomena, it's only through observation and testing that we can determine if they are physically real. This is where organizations like CERN come in, conducting experiments to examine the existence of negative masses, much like those proposed by Farnes. The Square Kilometre Array, the world's largest radio telescope in development, could also be instrumental in advancing Farnes's theory. Lewis believes that pushing the frontiers of fundamental physics, although initially esoteric and bizarre, ultimately benefits our everyday lives. Aside from these theories, scientists have advanced another compelling argument. The visible universe, which includes Earth, the Sun, other stars and galaxies, is composed of protons, neutrons and electrons bundled into atoms. One of the most surprising discoveries of the 20th century was that ordinary or baryonic matter accounts for less than 5% of the universe's mass. The rest of the universe, on the other hand, appears to be made of dark matter and a force that repels gravity known as dark energy. As previously stated, scientists have yet to directly observe dark matter. It has no interactions with baryonic matter and is completely invisible to light and other forms of electromagnetic radiation, making dark matter impossible to detect with current instruments. But scientists believe it exists due to the gravitational effects it appears to have on galaxies and galaxy clusters. Stars at the edge of a spinning spiral galaxy, for example, should travel much slower than those near the galactic center, where a galaxy's visible matter is concentrated. However, observations show that stars orbit at roughly the same speed, no matter where they are in the galactic disk. This perplexing result makes sense if the boundary stars are subjected to the gravitational effects of an unseen mass, dark matter, and a halo surrounding the galaxy. Some scientists believe that dark matter's effect on the universe could be clarified by changing the fundamental principles of gravity. They suggest that there are various forms of gravity and that the gravity that governs galaxies on a large scale differs from the gravity that we usually experience. On the other hand, dark energy is even more mysterious, and its discovery was a complete surprise. Physicists initially thought that gravity would slow down the expansion of the universe over time. However, when two independent teams measured the rate of deceleration, they found that the expansion was speeding up. It's like throwing keys up and expecting them to fall back down, but they fly straight up towards the ceiling. Now scientists think that the accelerated expansion of the universe is caused by a repulsive force generated by quantum fluctuations in empty space. This force is growing stronger as the universe expands. Many scientists believe that the known properties of dark energy align with a cosmological constant, which is a mathematical patch that Albert Einstein added to his theory of general relativity to make his equations fit with the idea of a static universe. Einstein assumed that the constant would be a repulsive force that counteracts gravity, keeping the universe from collapsing in on itself. But Einstein later discarded the idea when he discovered that the universe was expanding. So, adding dark energy as a cosmological constant could almost explain how space-time is being stretched apart. But scientists still don't know why the strange force exists.